Hi and welcome. I'm trying to learn particle physics, today neutrinos, and after we've done it, we're going to do stretching. And if you participate in stretching, then it's not at your own risk. The mystery of neutrinos. The ghostly neutrinos are among the most mysterious particles predicted by the Standard Model. Their weird, shape-shifting nature could be the key to physics beyond it. Okay, there's the Standard Model that says there are around 20 different types of things inside of each fermion, and fermions are all the matter which exists. That is the part we understood. So that is how we understood it, we don't know if it's right. And there are these neutrinos. Electron neutrino, muon neutrino, and tau neutrino. So inside of each fermion, they are inside of each atom, inside the, I don't know, there are the electrons, the muons, and the taus, and now the electron neutrino, the muon neutrino, and the tau neutrino. Neutrinos are notoriously hard to pin down. They have no charge, almost no mass, and can pass through matter by the millions without leaving a trace. They have no charge, they are neutrinos, almost no mass, and can pass through matter by the millions without leaving a trace. Is there any type of particle which is able to pass through things without leaving a trace if it is charged? The first inkling we had that they were out there came in 1930, when physicist Wolfgang Pauli was struggling to make sense of the decay of certain radioactive nuclei. Okay, in the 1930s there was Wolfgang Pauli, and he was struggling to make sense out of the decay of certain radioactive nuclei. Okay, he had the radioactive material, pronounced uranium, and he didn't understand how it all was decaying. One day he had a kilogram, and the next day he had only half a kilogram, and he wasn't understanding how it was. No, I don't know what this meant here, but it's a very thing. When an atomic nucleus undergoes beta decay, it morphs into a daughter nucleus, emitting an electron in the process. Okay, there's a nucleus of atoms, and now there is beta decay, whatever that is, and then something is morphing away. Well, it morphs into the daughter nucleus, but it loses an electron, emitting an electron in the process. But the two decay products went in directions that seemed to violate the cast iron law of conservation of momentum, suggesting some third particle was indeed to make sense of the results. Okay, whatever, it wasn't probably decay. It was Wolfgang Pauli's big thing to think about. The tiny, chargeless particle Wolfgang Pauli dreamed up was subsequently called the neutrino, the little neutral one. Okay, and now he said there has to be a third particle interventing in that, because just by itself they are not doing it, there is something third interventing. And was spotted in the white in 1956. So this neutrino was found in the 50s. Over the following decades, experimentalists gradually worked out that neutrinos came in multiple types or flavors. Okay, flavor seems to be just the name for it. I don't know why. And we found three: the electron, the tau, and the muon neutrino. Were the neutrinos that Pauli had predicted? Maybe there are more. Pauli had predicted with an intimate connection to the electron, but also those with similar relationships to the electron's heavier cousins, the muon and the tau. These three neutrinos neatly slotted into the Standard Model, and that appeared to be that. Okay, he had some stuff of radioactive material that was decaying, and then he didn't found, as he wanted, the daughter nucleus and the other thing, but someone else had intervened, so there has to be a third particle, and there was not just an intervening with the electron, but also with the muon and the tau. So there is the electron neutrino, the muon neutrino, the tau neutrino. Now we're having in the Standard Model three things more. This is all very well and good, but the nature of neutrinos makes them incredibly difficult to snare and study. They don't feel electromagnetism or a strong nuclear force, which means they hardly interact with other material at all. Catching neutrinos is a matter of patience, of watching long enough with big enough detectors until enough of them interact. Generally, these experiments take the form of huge nets whatever it is, of incredibly pure atomic liquids, where the neutrinos presence is registered through the emission of pulses of characteristic scintillation, light caused by the passage. I once read something about a neutrino detector. There's water, there are a lot of photon cameras, and when it happens that one of them sees when such a neutrino, I don't get it. Generally, these experiments take the form of huge vats of incredibly pure atomic liquids, where the neutrino's presence is registered through the emissions of pulses of characteristic scintillation, light caused by their passage. As it happens, we have a massive source of neutrinos right next door in cosmic terms. The Sun is a nuclear fusion reactor, powered by beta decays that pump out electron neutrinos by the billions. Some of these come our way, passing straight through Earth on their journey out into the wider universe. Nuclear power stations also pump neutrinos out in abundance. Let's just read the last part again. I bet it wasn't particle physics, but no. The nature of neutrinos makes them incredibly difficult to snare and study. They don't feel electromagnetism or the strong nuclear force, which means they hardly interact with other matter at all. Catching neutrinos is a matter of patience, of watching long enough with big enough detectors until enough of them interact. Generally, these experiments take the form of huge vats of incredibly pure atomic liquids, where the neutrino's presence is registered through the emission of pulses of characteristic scintillation, light caused by their passage. As it happens, we have a massive source of neutrinos right next door. In cosmic terms, so the Sun is an emission of neutrinos. The Sun is a nuclear fusion reactor, powered by beta decays that pump out electron neutrinos with a billion. Some of these come our way, passing straight through Earth and on their journey out into the wider universe. Nuclear power stations also pump neutrinos out in abundance. This is also particle physics part. If you are here for particle physics, you can currently repeat the next part of particle physics. Maybe we have all the answers to all questions. We will stay now here, and if you stay here, then you're doing the stretching. If you stay and participate in the stretching, then it's with the arm risk. Good as it stands, the breathing hand from the outside. And breathe out, we go up to one side. Breathe in and up the rib cage. And out, back into the middle. Again. Out. In and up the rib cage. Out into the middle. Up, stop. Breathe again in. Now it sees the actual uprise, now exercise. And out, and one hand slides down the leg, and the other shoulder stays down. Breathe again in. And out, taking one arm over. Breathe in and open the cage. And off. Moving in. And out, one down. Moving in. And out, one arm over. Open the cage. And before back into the middle. Now the feet are lying together. Now the feet stand together. We are doing the aeronautic aerobatic airplane, the breathing energy also. Then breathe out and one hand comes down. And breathe in and reach. Breathe out, hand up again. Again in. And out and one hand down. Breathe in and reach. Out one hand up. And down. Next exercise. Extending shoulder with wide part and doing forward shoulder circles. Back with the shoulders and up, in front and then down. One more time. And now backwards and front, up, back and down. And now we're breathing in, lifting the shoulders up. Left the foot down. Back in. And out. Back in. Now the apple plucker, arms up, and reach always with one arm high up. Pretend to take an apple hanging high on an apple branch, to turn it a bit around, and then to pluck it. And the last one, and now the shifter. Arms up to a T, legs wide apart, we're breathing in. And out we're going over to one side, just as the other part of the body. Breathing in. Out over to the other side. Again in. Out. Again in. And out. Again in. And out, we're leaning onto our knees. The buffalo fighting its hangover. Breathing in. And out, one shoulder in front. Again in, shoulder back. And out the other one in front. Again in. Out. Breathing in. And out and we're hanging down. We're doing the Niagara Falls. Just breathe in. And out. Again in. And out over to one leg. Breathing in. Then out over to the other leg. Breathing in. And out back into the middle. Breathing in. And then out and we're closing the feet and we keep on hanging down with salto angelo, no closed feet. Just breathing in. And out. Again in. And out. Again in. Now out we're coming slowly with our back up and making it to the backwards shoulder. Now garland holds the toes only to the outside. Having an overlap space between the heels, so we're breathing in the outside. And we're breathing out, we're sinking down, we're placing the elbows against the inside of the knees. And we're breathing in and we're straightening up with the back. And breathe out and we're coming up with the back. Breathing in. And out again down. We're going to straighten up. And breathe out again with the back up. Again in. And down. Now we're going straight up. But we're coming slowly in one straight line upwards. We're ending with a trunk igniter, the legs wide apart, we're breathing in. And out. Again in. Out. Again in. Out. The last strong breath in. Out. Again in. Out. Now we're in. Out. Again in. Close the legs. And breathe out. That was the stretching. I thank you very much and until next time.